Good morning, everyone. We're going to start today with the debugging and testing with Max. And remember, if you have any questions or comments, we have the mic here. Okay. And another comment, please go to the Google Doc and put your initials in the rules, the participation rules, please, if you haven't done that. Okay.
Okay, good morning. Before we start with the lecture itself, I have some additional example material that's not related to the pytest-cov repository in this S3 2026 lectures repository that you cloned yesterday. And maybe you just pull there on the main branch to get updates. Some things I updated since then. And there's a testing directory here where I have two examples. One is a small repository. You should know from yesterday what it contains, right? There's this nice small function we wrote yesterday, or very similar to what we wrote yesterday. And this is what we are going to use mostly for the examples, for the simple unit tests. And then I have some more examples for different kinds of situations we might end up in testing scientific software here that we can run during the lecture as a demonstration. Okay, but first a little introduction. So what is unit testing and later about debugging. Then the main part will be learning how to use PyTest, which is the testing framework that is the standard solution nowadays for doing unit testing in Python. And then we will briefly talk about some more advanced concepts of testing. So computing test coverage, which is a metric to tell you how much of your code was actually tested during the execution of your unit tests. And then I don't know how it is for you, but we have some software that isn't really meant to operate in isolation. It interfaces with other services. It may even talk to real hardware. And writing tests for these kinds of software pieces is always a bit tricky, right? You can't give your CI system the real piece of scientific equipment to run unit tests against the real hardware. You have to mimic the API or the interface of this hardware to run your software tests, and this is what we call mocking or digital twins or monkeypatching in some cases, where you replace a real piece of hardware or an external service to your software with something that looks a bit like it, that is enough to let your side of the software run its tests, but that's not the real thing, and you can have it in your laptop, you can have it on the CI server. Then there is doc tests, which is if you have in your documentation, you can have code snippets, example usage of your software. You should execute these examples to see if they actually work. Often documentation grows older over time, and maybe you change some of your software and the examples are not updated and then they break. And doc test is a nice method to see that also the examples you have actually still work with your software. And then we go into the debugging business. Same disclaimer as last time. With Python, it's a bit more dangerous to copy because maybe some spaces are missing, and in Python the spaces are very important. So let's talk about what unit testing or software testing in general is. So maybe you have already noticed that, I mean, we all need to verify that our software actually does what it's supposed to do, right? You need to check your computations, you need to verify that what you wrote is actually what you intended to do. And maybe you opened IPython, you imported your stuff, you ran it once, you saw that it worked, but doing this manually is extremely tedious. You have to repeat the same manual steps every time you change something or update software dependencies. You maybe want to do this if you are developing a library or you are planning to upgrade for multiple versions of Python. Maybe you have users on a different operating system, then you start doing the same manual steps on a different operating system. And if you don't automatize how you run these tests, then it will just result in you not running the tests most of the time, and that will mean changes can break the software. So the main thing is we need these automated tests to verify our software. They need to be relatively easy to run. At least a base layer of the tests should be very fast so that you can execute them often. And then maybe you have an additional layer of tests that take a longer time to run that verify larger pieces of your code. But at least this base layer of tests for single functions for maybe small little modules of your code, these should be very fast. And this is also how we categorize these tests. So we have basically three sections here. Unit tests are the small tests that just take one function, see that when you give it inputs, where you know the expected result is actually returned. And maybe they grow a little larger than this, but that's the basic idea. Testing little units of your code in isolation. So it can be fast, it can be fine-grained, and doesn't suffer too much from interactions between different parts of your code. And then this is exactly what the second category is about. So integration tests is if you have a large software package, then it uses all different kinds of functions from all over the code, right? And then you run integration tests that test like one big feature, one analysis maybe, or one task of the software, and that will use all of the different units that are in isolation, hopefully already tested. But then you need to test the interfaces and how you plug them together, the different parts of your software. And then the third kind, performance tests, is not just testing the functionality, that it does the right thing, but also that it's fast enough for what you need to do. And today, in this lecture, we are mostly speaking about the first kind of test. And these, as I said, they test the single units of code, and it's a bit hand-wavy what a single unit is, but think of one class, one function, or even one method of a class. You do some setup, you test that this method of this class does what it is supposed to do, this function does what it's supposed to do. And these are basically like Lego building blocks to make sure that your whole software stack is functioning. And as I said, must be easy and fast to run, otherwise they are not run most of the time. And being able to do this, unfortunately or fortunately, has implications on how you organize your code. It's only simple to do unit testing if you have a modular code base. If your analysis, like we started in the pytest-cov repository, is a single script of 500, 300 lines of code without any functions, the only unit you have is the whole script. And then you're running one integration test of this whole script and not unit tests of the single functionality. So being able to do unit testing means you need to organize your code in a way where functionality is isolated in small functions that you can test in isolation. Put numbers in, where you can, for example, by hand calculate the expected result, and then you can unit test your functions. So what are good unit tests? I have here a list of criteria you can evaluate your unit tests from. First of all, they should exist, right? Otherwise, we can't really work. Then, of course, the correctness aspect of it. So the test should make sure that the code that is tested behaves according to your requirements or specifications. Then for the overall unit test suite, we have the completeness criterion. So you should cover all of your code. And we will see how we can actually compute this later in the lecture. And one of the most important criteria is the readability. You need to make sure that the test is testing what it is supposed to test by inspection, by code review. Because otherwise we are ending up in the situation of yesterday. We get a recursion error, right? Because we cannot write tests for our tests to make sure the tests are correct. You need to have them readable, easily understandable. Maybe if you are in a formal software development environment, you have use cases or requirements, and then the tests should be very close to these use case scenarios so that another developer can look at them and make sure that these are really testing what they are supposed to do. And good unit tests also serve as documentation, right? You shouldn't write tests that use some internal features of your module, maybe the private methods, right? You should write unit tests in a way that they demonstrate how your software is meant to be used. Because that's what the users care about, right? You write little examples mainly, and in between of the example execution, you test that the results are actually what you expect. And what is often very hard to achieve in like numerical code bases is resilience. For example, we have simulation code that relies heavily on Monte Carlo methods, and then it's really hard to unit test if the code under test is intrinsically stochastic. So you need to fix the random seeds, you need to make sure that you are inside of a probability envelope of what you would expect, but then it can still fail in 1% of the cases or whatever, right? So in many cases, it's relatively easy to have resilient tests, but sometimes, for example, if you interface with an external service, if you have these numeric data codes or numeric stochastically simulated codes, then it's sometimes hard to achieve resilience. There are frameworks or parts of the language that are available in basically all languages, all modern languages, and I gave you some examples here. So for Python, there's unit test in the standard library, but it's much less user-friendly to use, I would say. So there's the pytest module, which is a third-party package, so you have to install it from PyPy or from Conda. It's not in the standard library, but it's the de facto standard solution nowadays to do unit testing in Python. For C++, there are two big popular libraries. So there's Catch2 and Google Test. I don't have a strong favorite. Google Test is a bit more widely used. Catch2 is a bit more modern and fancy with more bells and whistles, maybe. I think there's also the Boost testing framework. If you're already using Boost, then maybe the Boost testing is a good idea. For Java, there's the one main contender is JUnit. In Rust, it's just part of the language, so you can add specific macros that mark functions as test functions, and then you can execute them as tests. And Julia has a test module in the standard library. Okay, and then for the integration tests that I think Carl will speak about a little in the lecture after this one, it's you have your units, your little functions. They are tested by the unit tests, but then of course the interfaces, how you put them together, is important. Also, you need to make sure that they are working together, and that can be a larger module, a command line application, a web service, a certain flow. What you expect your users to do with the software. And these can go very, very large. So for example, for our software system, we have integration tests that run in a Kubernetes cluster, and we spin up, I think, 50 different Docker containers that contain different services of our system, including basically a data center simulation with storage endpoints, compute nodes, where we submit computing grid jobs and then run analysis in these computing grid jobs. And that takes on my laptop maybe 15 minutes to get the system up. I can run the integration tests and then I shut it down again and start fresh after So these can get very large, very complex, but you should still strive to make them run repeatedly, reproducibly, so you can run them in the CI. Maybe not on every merge request, maybe not on every push, but in a nightly build on the main branch, for example, or every week on the main branch, or just before you make a new release to check that everything is still working in these more complicated setups. And then the performance tests, as I said, we write scientific code. We shouldn't waste resources on our computing centers, right? So speed is always a concern. And you can make performance tests of your software. These mostly work by executing like a standard analysis or some function in a controlled way, measuring how long it takes. And then there's several tools that let you record over time in your Git history how long this has taken. And then you, for example, see if a commit results in this function being 2 times slower than before. You can do something, open an issue, try to fix it. I'm not going into detail here how this works. You mostly also need dedicated hardware for this because performance testing is a bit hard on these shared CI runners on GitHub because depending on how many other people are running jobs, the performance of your code might not be reproducible. So you need mostly one dedicated server for running these performance tests, and then you're in the category where it's mostly not worth for your personal projects or for smaller projects. Okay, I already showed you the example Fibonacci function, right? We are going to use this again. You know it from yesterday, I guess, so not too much to explain here. And we are going to write some basic unit tests for this function. And let me introduce pytest. So as I said, this is the standard framework nowadays for Python, not in the standard library, but really the de facto standard. And what you do most of the time is you run your code, you compute something, a result, and then you use the assert statement to check that the result is what you expect. And we will see some examples. And you write these tests. PyTest has a way of discovering automatically what part of your code is test functions by naming conventions. So you have Python scripts that start with test underscore or end on underscore test.py. The functions itself are called test something, and the methods are also named test something of classes that start with test. So it's everything basically that starts with test somehow is treated as test by PyTest. And then I gave you here the link for the documentation to look later. So if you do not use Pixie, if you just use a Python project, you would add this to your optional dependencies like this. So also the test name is convention. These optional dependencies can be installed by adding square brackets and then the name of the optional dependency group. So if you are in local development mode and want also the dependencies needed for testing, you would do pip install -e dot the local directory and then in square brackets the test. Or if you install from PyPy, you can also add the square bracket test after the module you want to install. For Pixie, we will do it in the example folder later, but you can add a feature called test, and you say that you depend on PyTest in the current version 9.0, and then we add an environment that relies on this test feature, and we can use it to run PyTest. And then Pixie also has this concept of task that was introduced by Vincent, and we have, for example, one task that relies on the feature test. It's pytest, and then we can just run Pixie run test, and it should execute our tests. Maybe let's try this out in this Fibonacci repository here. So at the moment, I think there's nothing yet for Pixie in here. Yes, there is. So we have already added this. We have a feature for Python 3.14. We have a test feature that depends on PyTest and another library I will introduce later for measuring the coverage. And we have the environment for testing in Python 3.14, which depends on both Python 3.14 and the test feature. And we have a task here that's test, which calls pytest. And then just for convenience, I added one for less typing where it specifically runs in this Python 3.14 environment. I think this is, if you only have one environment, this is not needed. So let's check Pixie run test. What? That's weird. In default. Do I need to? Oh, it's not in the feature. Pixie feature test.tasks. Yes, okay. So if you need for task special dependencies, then you need to specify that this task lives in a certain feature. And then it runs in 20 milliseconds, whatever. And it executed our test. And then let's look at this first simple test we have here. So we have a very simple test. We import our Fibonacci function from our module, and then we test the first two numbers. Yeah. So we compute that the first two, and we check that the expected result is there.
Do we have to make comments on the test function? My question was, do we have to make some docstring on the test function inside?
Would be nice to your fellow developers to explain what this test is meant to do. I mean, if it's this size, sure, maybe not needed, but yeah. I mean, for our larger integration tests, we have a big docstring explaining what use case or what scenario is tested in this test, and it relates to our documentation. And yeah, in general, yes. Yeah. Let me just close this. Where is it? Okay, yeah. So here we are, just for people later checking the documentation, the slides, basically what we just did now. And maybe you were wondering why I put this import inside of the test function and not at the top. And if you have a more complicated library, you might actually break your code in a way that the imports themselves fail. And so the idea here is that if you would put it at the top, then the code in PyTest to collect all your test code would fail because it imports your test modules to look for these test functions. And if already the import at the top fails, then this collection mechanism fails and not the individual test. So the idea is if you put the imports of what you are testing inside of the test code, the collection of PyTest works, but then the individual test will fail if the import is not possible or not found, or there's some code that breaks the import. That's the only difference. Your test suite will fail either way, but if you have the import inside of the test function, you get more information on what exactly broke instead of a big red error screen that the PyTest test collection itself has failed. And then the first more advanced example I want to show is yesterday we realized that this code is not very user-friendly, right? So if I do and I do this, I get an error, right? We added this user-friendly error that n must be greater than 0. And this is also part of our interface now. We want to make sure that we don't get this ugly error we had before. So before we added this message here, we got this maximum recursion depth exceeded error, which is not very user-friendly, right? It doesn't tell the user that there was a mistake in the input, that it's not just not supported. So what you can do is you write a test that makes sure that you actually raise the correct exception in these cases. So you should not just test the expected inputs, but maybe also how your functions react to unexpected invalid user input. And we expect a nice error, so we can do a functionality of PyTest that we expect an exception to be raised, and the test will fail if this exception is not raised. So we expect a value error with, and now we can even say what message we expect. So we say n must be 0. And this is a regular expression. I don't know if you're familiar with regular expression, but it's not checking really identical, that the message is identical, but it's matching using a regular expression here with the message of the exception. So then we call our Fibonacci number function with the -1 input, and I will move the import here. And this test will now fail because I still have the code that will result in the recursion error. Yeah, so we get the wrong exception, so the test fails. And if I fix my code again to provide the nice error message that matches the conditions I defined in this pytest function. Oh, okay, now the message doesn't match. You see, exactly, there's no space. And now it passes. You see it doesn't have to be identical, but the part you specify has to appear inside of the string, and you can add these regular expression modifiers to do more complicated matches. Yeah, but this is how you would test that your code, in case of invalid inputs, in case of some error condition, raises the exceptions that you want. And then I already said we are writing numerical computation code, right? And we are doing computations here. Can somebody in the room explain why this test fails? Why is 0.1 plus 0.2 not equal to 0.3?
Because they are represented as a float.
Yes.
There's no really 0.1, but 0.1 of
Exactly. So if you type 0.1 and 0.2 in Python and many other languages, what you actually get is what we call an IEEE float 64-bit number. And numbers that are not representative in the 64 bits you have, they will be rounded to the next number that is being represented. And it happens that the next number that's representable next to 0.1 is slightly larger than 0.1. And 0.2 should be exactly representable, I think. And then the 0.3 is not representable again. But the number that is closest to 0.3 is slightly smaller than 0.3. So 0.1 plus 0.2 is slightly larger than 0.3, and the next number that's really close to 0.3 is slightly smaller than 0.3, and then this check fails. And there's this website here, which explains the background a bit. For many of the computing languages, and it lists for many programming languages what the behavior is and how you can work around it using some correct or some unlimited precision libraries. And I have this example here. So in the examples directory, there is test floating. Yes. So 0.1 plus 0.2 is not equal to 0.3. And maybe we now go a bit already into the debugging topic. Like we could see we can expect what happens here if we do -- pdb, which will dump us into the Python debugger exactly where the exception happens. And then we can do things like looking into what exactly we have here. And we realize that 0.1 plus 0.2 is this 0.3, a couple of zeros, and then the 4. And the reason for this is if you look really closely, so we do 0.1, and then we format to 32 digits. 0.1.34f. And it's not exactly 0.1, it's a little more than 0.1. And 0.2, oh, it's also not exactly 0.2, it's also a little more than 0.2. But then 0.3 is rounded to something slightly smaller than 0.3. But the addition of these two numbers will be done exactly. So you round first to store the number in memory, and then you perform the addition as exact as possible. And this is why you end up with a number that's slightly larger than 0.3, even you did 0.1 plus 0.2 in your code. And what you basically have to remember is what kind of precision you can expect from these floating point computations. And the rule of thumb for simple operations is that if you use 64 bits of float, you get 15 to 16 digits of decimal precision. And everything after that is just the rounding errors of the software. If you do many of these computations, these rounding errors can stack up. If you do 32-bit floating point computations, maybe because you're using a GPU where this is much more efficient, or you store data on disk and wanted to save disk space, or it's faster, then you only get 6 to 7 digits of precision with the 32-bit numbers. Okay, so how do we fix this? Sorry, wrong file. This one below here, so let's comment this out. You say that this is a floating point operation, and pytest has a helper function for this, so you say we expect this operation to return approximately 0.3. And this approximately has a default setting for the allow tolerances that work with these floating point operations. You can, if you know that you have a computation that suffers more from these rounding errors, or that's imprecise, or that relies on these random number generators, Monte Carlo methods that I mentioned before, where you expect a much larger deviation than what you get from these floating point computation errors, you can get a relative tolerance and an absolute tolerance. And I see that the example in the docs is even exactly this, right? The 0.1 plus 0.2. So you could even say that if you have a larger margin of error, you do something like 0.2 absolute deviation or relative deviation. You often need to add the absolute deviation if your expected value is 0, because then the relative deviation will just be undefined, and then you need to tweak the absolute deviation. And this one passes. Then many of us will be using NumPy to do these computations, so not just on one value, but on arrays of values. And then there are a couple of helper functions in NumPy for this kind of testing. So very similarly to the pytest approximate, you have assert array almost equal. And there you can also say, okay, you do your computation, you define the values that you expect, and you define decimal precision, how many digits have to match for the test to pass for each of the elements. And you have, I think there's like 10 or 15 of these different helper functions in NumPy for different use cases. You can have a look here in the documentation. But the ones I use the often are this assert all close, where you just call your function and then have the expected results and a tolerance, or this digit precision. You can also run this. So here in floating NumPy, yes, so we have this setup here. And for the, I mean, this is basically looking up on Wikipedia what the expected numbers are for the sign computations, right? We put in 0, half pi, pi should be 0, 1, and 0. Or you remember this from your high school lectures. Maybe let's go into a shell here so I have less to type. The minus v is a nice option that gives you a little more detail. So if I drop this minus v, I just get 2 little dots here for each module, how many tests were executed. And if I add the minus v, I get each test function individually listed, what happened. If they fail, you get more detail. One recommendation I would also give you is that if you are writing tests, break your code to see if the test actually catches an error. So let's imagine we don't test the NumPy sign, but we have our own faster implementation of sign, whatever. But by accident, we computed the cosine. And then these NumPy testing helpers really help you dig down on the problem, because the output you get from these is very, very helpful, right? So first you have the test failure here, and the error message is just that the errors are not almost equal to 15 decimals, which is the precision we have defined, but then it even summarizes what happened. So we have a mismatch on all of the 3 elements of the array. And then the mismatch is, we have a value of 1 actually, but 0 was desired. We have a value of basically 0, right? So this is 6.1, but to the minus 17, which is again this floating point precision, right? I told you had 15 to 16 digits of precision. So for all intents of purposes here, this is equal to 0. And then minus 1 we desired 0. And again, then in the difference, a summary of both the expected and the actual results. And with the correct function, it passes again. I realize this is a bit niche now, that the audience of this school is a bit wider than in the years before, but already yesterday we talked about a bug in this AstroPy unit system, right? And there are other libraries that are more general for unit handling. So there's pynt in Python that allows you to attach units to NumPy arrays and do efficient computations with different units, and it will automatically in the background convert between compatible units and for example, if you divide a length by a time, you will get an array that has the physical quantity of speed, and it will correctly handle these units. And there's also helper utilities in AstroPy and in pynt as well. If you do tests on these quantities, so you have a speed and a distance in meters per second and kilometers, and you expect if you go 1 kilometer with a speed of 10 meters per second that it takes you 100 seconds. And then you can test that AstroPy units is close of this computation is close to 100 seconds. Again, is close because we are making these floating point computations. And aside from very rare cases, you should never test exact equality with floating point numbers. You should use these tailor-made functions that know that there is limited precision with the floating point numbers and do the right thing, have these tolerances, and only fail if the tolerances are exceeded. Yeah. And then we are going into the territory of more complicated tests. Many tests maybe need some input data, or they interact with your system, or they need to store output data. I think that was a question we had yesterday, how to deal with tests that store data on disk during the test execution. And PyTest has a concept of fixtures. And these are things that provide some input data or some boundary conditions to your test. You can prepare an environment, you can modify what is run, and you do this by defining a function that returns something or that sets something up for your test. And you have to decorate it with this pytest-cov function. And the scope is important for how often this fixture is executed. So if you have two tests that use the same fixture, if it's scope session, it will be executed once, and exactly the same data will be provided to both of these tests. If the scope is function, then for each test, the function will be executed again. Right? You get a fresh copy of the data. And this is important in cases where you, for example, have mutable data structures in Python. So if we go here, which one is this? I think fixtures and this one. Yes. So we have two tests, right? The first one just checks that the data is of length 3, and then the second one checks that the data, the first entry is 1. And we get the exact same object here. I could show this to you by doing this, id some data. At least I think that will work. And by default, if all of the tests are passing, PyTest won't show you all of the output that your code generated. It will just say everything fine. But there is an option -s to not capture the output, and you can see here these two identities are the same, so the object is really identical. And what I could, for example, do here, I could introduce a side effect of this test. So if I modify some data here and put some data 0 is 2, then the first test passes, but the second one fails because the first test modified the input data. And in this case, you would want to change the scope here to function, and then the second test would get a fresh instance of the data. So this is how this scope argument works for most of the things. These things, it's maybe not necessary, but if you have something expensive, maybe a database connection or some initial setup in a database you want to do for the tests, you would put it in a scope session that it's once at the beginning and can be used by all of the tests. If it's simple data, or even where you want to be sure that each of the tests gets a fresh instance of something, you need to use the scope function. Yes?
You gave to the function is a function.
Yeah, sorry, this is maybe a bit too magical to understand immediately. So how this works here is that this fixture decorator registers the fixture in the PyTest machinery, and then PyTest sees that the test has an argument that's the same name as a known fixture, and it inserts the output value of the function. So you don't really give the function. You register the fixture with this decorator, and then the match is done by name. The argument name is matched to the function name. I didn't give any argument here, right? I defined an argument, but the value is inserted by PyTest during this test execution automatically.
The name of the argument is the same that the function you define.
Yes, so if I, for example, have a typo, it will say that there is not a known fixture of this name. Fixture some data is not found.
It's just because you used the I forgot the name, the arrobas in front of the function name.
The decorator, yes.
Decorator, sorry.
Yes.
Yeah, thanks.
And if a test function modify the data, if another test function is run after, did it run on the initial data or on the modified data?
That depends on the scope. If the scope is function, the fixture function will be run again for each test, and you get a fresh copy. But if you say session, then it's only executed once, the result is stored, and all of the tests get exactly the same instance of the data, and this test will now fail, right? I modify the data in the first test, and the second test relies on the initial data, but it has been changed, so it fails.
Maybe you should mention what is the order in which tests run.
Yes. I think the order is just, I mean, you should never rely on it, is maybe the main information here. There are some cases where you might want to do this. I would discourage this, but there is a plugin for pytest where you can add a decorator to define ordering of these. It gets very hard to reason about if you have a large project, you want to run many tests in parallel, for example, and then the order is really just random because the next free thread that can execute a test will just pick one test to execute. So your tests should work in isolation. They should never rely on another test doing something. And one of the main reasons for this is that you would want to run tests in isolation for debugging, for example. So I will show a couple of examples later. But I can, for example, just execute the second test by doing -k also. -k is for keyword. And then it will match the test function names with what I gave here. And it just executes one test. And suddenly it passes now, because now the first test didn't run and didn't modify my data. But if I run all of the tests again, it fails. So the same test now passes when it's run alone, or it fails if it's not run alone. And this is not a situation you want to end up in, right? And now also with only the first one. And you can't just define fixtures yourself for what you need, but there is a large number of fixtures already provided by pytest. For example, to create temporary directories where you can store your input or output, you can test that code you have actually prints messages you want or performs the logging you want with these capsys or caplock fixtures, which during the test execution capture the output, and then after the test you can inspect what they captured and you can make sure that the messages you want were actually printed. For the monkeypatching part, there's this monkeypatch fixture, and I have a couple of examples now here. So we have a greet function that takes a name and then just says print hello, and I didn't update this example. Shame on me. So let's fix this quickly. So we are at the S3 School 2026. And we expect S3 School 2026. Yes, so we run our code, and because we have this capture capsys, we can ask it what was during our test execution printed to standard out and standard error, and we can make sure that the standard out is the message we expected from our code. Maybe let's introduce an error here, so missing comma, for example. Yeah, so it even nicely here underlines exactly the difference between the two strings we have, right? We can immediately see where it went wrong. And now the test is passing again. Similarly, you might not use print statements. It's also a very general recommendation. As soon as you have something that's of wider interest or that's a library, please don't use print statements. Use this logging framework from the standard library. And we can add very similar tests here to the logging that is emitted by our code. So we have this very important work function, and it gets its own logger. It prints us info messages, and we can now use this caplog feature and say we are only interested in info and above messages. We call it, and then we want to see that we actually created 2 logging messages, and for each of these messages we make sure that the level is indeed info, and we could also check on the messages themselves and that it's really what we expect here. Yeah.
In your example, the caplog was not defined, and yet you use it?
It's one that PyTest defines for you. So if you are using PyTest to run the tests, you have access to it. You can just put it into the argument again. It's one of these predefined. Capsys as well, right? Capsys and caplog are the fixtures that come from PyTest built-in, and you can find all of the built-in ones here. There should be the built-in fixtures somewhere.
Fixtures, right?
That will also list the ones I defined. So there should be reference guides, fixtures. Yes, here's the built-in fixtures. So there's a large number of different built-in fixtures you can use. I will show you some of them, which I think are often needed. And one very handy one, is this temporary path fixture. So if you have tests that do I/O, for example, you write a reader and a writer for your own data format, of you store your analysis results, and you will, in files, you want to make sure that this works. You can use this temp path fixture to store the files, and the nice thing about this is, opposed to the temporary file module in the standard library, if you use that with the context manager, it will automatically clean up immediately. But this one leaves the data after the test execution on disk, especially after failures. It's very useful to look into these files then and inspect them to see what went wrong. The temp path fixture by default has scope function. And there is a temp path factory. If you need other scopes, you can create temporary directories that are available for all tests in the session. So how does this work? You have, for example, again, maybe I come up with a different example here, since we are not all into AstroPy here. Let's maybe add matplotlib here. Oops. So just some simple example plot, and we store it. And then we can, in our test, call plot, and we say that we want to store it in temp path plot.pf, for example. And we could also see if we maybe can store it also as a PNG. And then we can for example, assert that at least the file was created, so that temp path/plot.pdf exists, and also the PNG should exist. And maybe we switch the order around here so that we actually maybe write 2 tests here. So test PDF, test PNG, right? So this should create this plot, save it to the specified file, and then we test for now only that it's created. Matplotlib in its own tests, it has functionality that you can compare the output to reference images, for example. If you really need to make sure that your plotting code produces the same graphics again and again, then you can store maybe the first execution of the test you just store, and then you save the image and in the Git history maybe even as a reference image, or you have a server with the reference data and you compare the output to the input, or you ask your favorite image machine learning model if the data is compatible or if there's a mismatch.
Excuse me, that means that Matplotlib has also some test framework inside?
Some?
Test
Yeah,
framework?
maybe, I don't know, 15,000 unit tests for all of their code, yeah. They are using pytest. Yeah. Now, all of these major libraries that are this widely used, they have extensive test frameworks. Maybe even the ratio of test code to actual definition code, function code is large. Yeah. I don't know if you know the SQLite project. It's a file-based SQL database. It's the most widely used database system in the world because many of the Android apps, for example, use it to store data. So they guesstimate that they have around 1 trillion SQLite databases deployed currently, right? And I think they have a factor of 1,000 between test code and production code. Okay, the 2 tests ran. And now you can look into your temp directory. There should be a pytest of your username. And then there's, we can maybe just look at this. So there's, for each iteration of pytest there is just an increasing number. And then there's a symlink to the latest one you have. So you can always look into pytest current. And then for each of the functions under test, you have also the different iterations if there are multiple, and the symlink to the latest one. So we could use PNG current. Sorry, I want to go in there and maybe just open my Explorer here. And look at the file. Yeah, and this looks how I would expect it to look. And if I really cared about how this looked like, I would need to write some code to compare this image to a reference image, or maybe it would be a better idea to split the saving of the figure and the creation of the figure, because then in your test you could inspect actually the figure object and see if it has the right graphs and the right labels in code, and you are not relying on the actual output of the graphics, but really that you created the right objects in the figure, right? Okay. And with external services or with resources in general, you often have to do cleanup steps, right? You acquire a resource, you use it, but then you also have to free it again. And if your tests uses resources that need these kinds of cleanup steps, you can use a fixture that is basically a generator expression yielding what you need to use, and you do the setup before you yield. Then you yield the object that should be used. Then the test runs, and after the test is finished, the execution continues after the yield, so the cleanup code is called. And I have the explicit version at the top, so you open a database connection, you give it to your test as a fixture. After the test is done, we close the database connection again. But in Python, all of these objects that acquire resources and use them and have some internal state that needs to be cleaned up again, they should always provide this syntax of the context manager where you say with a database connection, with database connect as connection, and then your yield. And regardless of how you leave this with block, the cleanup code is always called. So even if there is an exception, also the cleanup code is called, and yeah, this works very nicely for tests needing these resources that need some form of cleanups, that some memory freeing or a database connection closing, web request closing, cleanup of a temporary directory, whatever you can imagine should happen after you run the test and clean up. And then we had this Fibonacci test, right, where let's go back to the lecture examples, test Fibonacci. This here is not a very exhaustive test of the Fibonacci numbers, right? It barely scratches the definition. So what I would do is I would look for reference data. And I just copy it here. And these are then trusted Fibonacci numbers, right? Oh, sorry. And what I can do is I run my test on all of them. But I just define a single test. And how I can do this is I can say my test gets 2 arguments now, I or n and the expected number. And PyTest provides a special marker here, so I can say mark.parameterize. And I define as a argument names which of the parameters of this function I want to parameterize, n and expected. And I provide data. And in this case, I enumerate the expected numbers. Enumerate takes an iterable and just adds an index. So for each iteration, I will get the index, I or n in this case, and the expected number. And PyTest will create automatically a test for each iteration over this data object. So what I can do now is I test that the nth number is the expected value. And if I now run the test, you will see that it generated a lot of test functions here for all of the different number combinations, and all of them are passing. If I break one of the numbers, then just a single test will fail and the others all work.
Is there a mechanism, as you showed yesterday, for catching? In that case, it could be along to estimate Fibonacci numbers, as you saw yesterday. And you use a decorator cache.
Cache. I mean, yeah. It's the same implementation from yesterday, I think. So I'm...
Oh, you
I mean, it was this fast, so I think it's in there. No? No, it's not. Then I maybe show you something else for performance testing. So you can ask PyTest to print, let's say, the 10 slowest tests. Durations. Oh, and these were all really fast. So let's maybe have too many open windows here. Let me close some of them. Okay. So let's add some of the higher numbers, right? These should take long. I don't remember, so I will enter something wrong, and if my code is correct, 38 maybe. And I should test 33, test 38. So let me, sorry, I need to remove, these are not parameterized now, so I need to remove the arguments. This takes long. Yes, so and now it tells us here, I mean, they failed, but you see, so your slowest 10 durations, and in this case only 2 because the others were so fast. We took 5 seconds on the 38 and 0.7 seconds on the 33. I can copy these values here quickly so that the tests are passing and are just slow. I think I copied the, no, that's correct. So they should pass now, but be slow. Okay, 4 or 5 seconds again. And now they're fast. And I didn't change my tests, I just changed my code. Tests are still passing. That's the reason why we have the tests. And if your library grows large, maybe it's a large analysis framework in your domain, in CTAO pipe, we got complaints by our users that some of the functionality is not interesting to them, but these functionalities, they introduce dependencies and they don't want to install the dependencies for stuff they don't use. So what you can do is mark some of the dependencies as optional, but then you don't want to run the tests for people that don't have these dependencies installed, right? And PyTest has some functionality here, so you can skip tests. For example, if a module is not available, so you can try to import NumPy, and if it's not available, it will just skip the test. Or you can test for specific operating systems. So if something is Windows specific, you can create a rule that if sys.platform is not equal to the string that's representing Windows systems, then the test is also skipped. Let's see if I have the example here. Yes. So I have NumPy installed. That's why the NumPy test was run. But I'm not on Windows. I mean, I am on Windows, but I'm in this WSL, which is technically a Linux system, so it doesn't run the Windows system. Or it's not technically a Linux system, it's a real Linux virtual machine on my computer. And sometimes, and we will talk a bit about test-driven development later, you expect tests to fail. For example, a user has reported a bug with a minimum example that's reproducing the bug, and you can write the test. But until you have solved the issue, this test will fail. And for these kinds of tests that you know at the moment are failing, but you already want to commit them to your Git history, you know that this test is the right thing to do, but it should be fixed at some point later, you can mark them as X fail, which means they are expected to fail. and they are specially highlighted and summarized, but they don't make the overall unit test suite fail if they happen. So if we do this, we see an X here, one test X failed, but overall, if you look at the status output code of pytest, it still succeeded. It returned a return code of 0. So this doesn't make the overall pytest execution fail. And if you have the option enabled that strict X fail, no. I'll just then if your test passes, although you marked it as X fail, your test will fail because the test behaved differently than you assumed. And that's a good idea to configure. I would personally, in a new project where you maybe introduce this, set this option here. You can define it in the Py project for every developer and the CI system. Yeah, I mean, these X-fail tests should be rare, I would say, but in some development workflows, for example, if you already know how you reproduce a bug, but you didn't have the resources yet how to fix it, you would add an X-fail test. And then when it's fixed, you can remove the X-fail and release a new version. And I already showed some of this, but you have fine-grained control with pytest about which tests run. By default, if you just call pytest, it will look around and use the configuration and the available files it finds to run all of the tests it can find. But you can have some options to limit the number of tests you want. You can just give a fully qualified name of the test function you want to run. So you give the module name that would run all of the tests in that module. Or you can give with 2 colons an individual function name, then it just runs this exact function. This is often a lot to type, and I showed this K expression, right, that you can just match the test names with the keyword with this partial name, which is often less to type. If you have done a large refactoring of your software that broke a lot of the tests and now you need to fix more stuff, it's often not helpful to run the full unit test suite, but you maybe want to fix one test after another. And there a combination of this last failed and max fail is very helpful. So you can rerun the tests that failed, and you stop after maybe 1 or 2 failures, and then you know what you need to work on next. So let's maybe demo this in Fibonacci. So if we break our code here, by not recursing and just always returning 2, we get a lot of test failures, right? Only the first couple of tests are passing, and all of the other ones, they get 2. So I got 4 passed tests and 12 failed, and I could rerun only the tests that failed during the last execution, and then I get the same 12 failures again. Or I could limit it to max fail equals 1, and then it will stop after the first failure and just show me the single test it executed. And if I would be silly, I could just do if n equals 2, return 2, return 3. And then the next test, sorry, no, I need to return 1 and then 2 in this definition. So it now executed 2 tests again, right? It started executing all of the past failures. The first past failure passed now, and then it stopped after the next failure. And now I realize how stupid I have been and just add the proper implementation. And all of the tests are passing again. And now it's a good idea to remove these filters and run all of the tests again, because maybe you broke the ones that were initially passing. And if you have a large library, or you are using PyTest also for your integration tests, which is a good idea. Technically, integration tests and unit tests are not different how you would execute them. You should also write them in PyTest, but they are just more complex. They have maybe more fixtures that need to be set up. There are more instructions, more complex things to test. But maybe they are slow, or you can mark them. So you can define in your PyTest configuration, in, for example, the PyProject.toml, you can define a list of markers, and then you can mark several of these test functions, and with -m you can do like logical operations, which markers you want to run. You want to run all the slow tests, or not the slow tests, or only the integration tests. So let's say that before we made this optimizations, so we had the marker slow, and before the optimizations we made, these 2 tests were slow, right? So we mark them slow.
That could be whatever level you want.
Yes, it's just a string. It needs to be a valid Python identifier, right? Because it's part of this decorator name, but other than that, it can be any name you want. So if I'm doing development, I would only run the fast tests, so not the slow ones. 14 tests. And then maybe it shows you, right? 2 of them were not selected because we had this marker selection here. Or I could just run the slow tests and have 2 tests and 14 pass. And you could have multiple, right? You could have like things that are marked integration and MySQL, for example. If you have a web service that can connect to multiple databases, you only want to run the tests against MySQL or PostgreSQL, or yeah. Okay. I touched this a couple of times now. Test coverage, what is it? So at the basic level, it's a very simple computation. Your test framework observes which lines of your code were executed during the tests. For Python, this is relatively straightforward because it's an interpreted language with lots of debugging information available. For compiled languages, you usually have to compile them with special compile flags so that the code is instrumented with information about the source code location that maps to that is then inserted into the binaries. This usually also means that you have to run in the lowest optimization level so that the binary code still maps to the source code and it's not, for example, optimizing away loops. So yeah, you have one job for measuring the coverage that compiles in this special compiler flags for measuring coverage, but then you run also tests with higher optimization levels and so on. And at the simple level, you basically get both overall information and then for the individual lines information which were covered. And if you have a GitHub repo, you can use this code coverage service, for example, or other services like this that gave you a batch, right? What is the coverage? 90% is quite good, I would say. 50% maybe you should work a bit more on getting there. And what you need is the pytest-cov plugin, and I think I added this already here to the Pixie environment. Yes, right? Yes, so here I have also the dependency on pytest-cov. And what this enables us to do is to ask for coverage here. And by default, it will just report per module how is the coverage here? Now it's very high because we have this parameterized test. Let's maybe cut this short, comment out these lines here, and maybe end after 2 here, or after 1. And I think it stores data between test executions. If I stop at 1, it shouldn't.
Line wouldn't get executed.
The recursion shouldn't be executed, right? Sorry, no, I misremembered how I implemented here. No, you're right. If I go up to 2, then this will be executed. So yes, so now I only have 90% coverage because the last line is not executed. You can get a nicer result here by asking it to store an HTML report. Out. Other way around. No, let me check my slides. COV report equals HTML. Okay. COV report equals HTML. And then it writes this HTML to this directory. And Python has a little web server. You can start like this. And then visit this in the browser, and you will get coverage information here. First page is a summary, but then you can click on the individual files here. And then you will get, for each of your code lines, you will get green or red, whether they have been covered or not by your unit tests. And this line coverage has some limitations. So what you really want to check maybe is not the line coverage, but the branch coverage. So do you see a problem with line coverage in this simple example here?
The condition is not met, stuff is not run.
Exactly. So maybe do other stuff breaks if we don't do stuff first. Right? So if during your test execution the condition is true, you execute all of the code and it might work. But if it's false, you don't run do stuff. Maybe that's a precondition for do other stuff, and then it would break. So you don't cover all of these branches. So line coverage is 100% in case of true, but not the branch coverage. And you can have arbitrarily many branches if you call a complex function like scipy optimize, which is used for fitting. I don't know, the pytest-cov example, did it use this for fitting or did it use iminui? Curfit, okay, yeah, very similar. Curfit as well has lots of parameters, right? It does a numerical optimization. So even if you have just the one line, the number of branches inside of that function you are calling is ginormous, right? So we can try to do this, at least for our own code. It will be still very limited in terms of the branches inside of the code we call. But you can say that you want to record branch coverage here. Okay, and it overwrote our coverage report. And you see that now there's a new label here, partial. And this means we have full branch coverage, right? There's 0 lines here that were only partially executed. If I remove the exception test here, need to restart this server. Then we now have one line that is not executed, and this if statement is partially executed because it was executed for the n greater than 0 case, but not for the n smaller than 0 case. Okay. And then we discussed a bit about these external things that you don't have under control. External web services that you are integrating, some mock-ups of hardware that you want to talk to, that your library is interfacing with. And if you need to do this for your own code, I would say this is a sign of lacking modularization and separation of concerns. You should be able to unit test your own code without monkey patching in most cases. Maybe for integration tests you would need it, but I would say if it's not for something that is external for your code, you should have a deeper look if you can avoid this kind of monkey patching. What do I mean with monkey patching? So for example, here I assume that we have code that interacts with some web service. For example, before connecting to it, it just checks if this web server is healthy. And we don't want to do these real web requests to an external service every time we execute our unit tests. So what we do is we monkey patch the requests library to not make a real request, but just to return a pre-made response here. So in the real code, we would really get this web server here. We would pass the JSON response. But in our monkey patching here, we just create a response object without ever talking to the internet, and we override here this get method of request with our simulation, right? And then if our code here is server healthy, calls the request.get, we have replaced it with our own implementation that doesn't talk to the internet. That's the idea here. Of course, it gets much more complicated if you need to spin up a simulator for real hardware or whatever services, external services your code relies on. And now that we have the basics of unit tests done, we can talk a bit about strategy, how you would start developing in a project that has unit tests or where you want to have unit tests. And one very popular paradigm is that test-driven development, which means that you actually write tests first. So you don't implement something and then write tests to check that it works, but actually you think about your problem, you plan how the API of your function should look like and what the responses and the inputs and the outputs should be, and you write the tests for this before you even start writing the actual code. And then you have a bunch of tests, or maybe a single test, that should all fail because you haven't implemented anything yet. But then you can already be sure about what you need to do, and you start the implementation, and do the minimum implementation that makes sense to you and that makes these initial tests pass, and then you are happy. And in case the tests are passing, you are now basically feature complete with what you plan to do, at least in this work time. And maybe you now review the code, you refactor it, and you can rely on the unit tests so that you still have correct answers. And this is very powerful. It's a good thing to try to do, but it's also something that's very hard to do in case, for example, you come into an existing project that maybe doesn't use unit tests yet, then you first need to add this base rock layer of unit tests for the existing code before you can maybe start doing some test-driven development. I would say this is especially useful if you have clear specifications. So for example, I maintain a library to read a proprietary data format of our simulation software, and I have the documentation for this data format that's a very clear specification. So I could write the unit tests, what I expect from reading this output file of my simulation code before I ever started writing code to actually open the file and look into it. It's also very helpful if you are investigating, debugging, trying to fix a bug. maybe your user or yourself, you noticed a bug by doing some computation, by doing some execution of your code. Transform this execution into a minimum reproducible example of this bug in the form of a unit test. Then you have the test first, and then you can start fixing it. And I mean, the test should fail because of this bug, and as soon as you fix the bug, the test should pass. That's a very nice way to debug using unit testing. And in general, it works better if you have a new project, not with a lot of already existing code that is not covered by tests. Okay, and the last topic for the testing is these documentation tests I mentioned. So in our Fibonacci code, we have usage examples in the doc strings that would get included in any documentation web pages, for example, we build. We should test that this actually works, that we don't show examples that no longer work with our code. I think most of you probably have run into outdated documentation that showed something that wasn't longer working, right? So this is a way to make sure of this. So we have here in our init, we have this example that uses the same syntax as the Python interpreter, right? So if I just start Python, I also get these three carrots here. The first lines in the interpreter. And this is exactly the same here. So I have these three lines here to mark this as an input code statement, and then the next line gets interpreted as the output this line produces. And PyTest can find these usage examples for you. And you see here, one of the tests now comes from the doc string of this Fibonacci.Fibonacci method, and it executed this line. And just to show you what this means, I can break it. So if we have the wrong output here, then this test will fail. It says the example produced 14. Sorry, it produced 13, but we expected 14. Okay. Any questions for the testing part of the lecture? How much time do I have left? 50 minutes, okay.
No, I have a random question about that last part. This is something that's happened to me a few times where I want to put an example into my function, but my function is quite complex and needs lots of setup. What's the right practice for making it? I mean, just don't use doc test for that, or is there a better?
No, you can have like a common prefix code, basically that's executed before any of your doc test examples. The hard part here is then how to tell your users that this is also what they need to do, right? And AstroPy has very complex doc test examples. They have their own plugin for PyTest that makes this a bit easier. For example, they have also for these floating point stuff, they have markers for the doc test output that this should only match to some tolerance, or that this output should just be ignored and just check that it doesn't raise an error. Yeah, but you can add this setup code for the examples with some common import statements, for example. That's maybe a good idea, right? To have, you say in your documentation, these examples all assume these 5 imports from my module, and then the examples should work. And I think this you can set up for doc test. Yeah.
We are actually into the coffee break.
Okay, then I stop here and continue with debugging in the exercise session, or okay.